Good afternoon, everyone. I'm Ben Gallagher, and I'm a lead physics programmer at Epic Games, focusing mainly on chaos physics within Unreal Engine. So today I want to talk to you about some of our recent work over a number of projects and how those features and improvements affect physics in Unreal and how you can use similar approaches in your own projects. So a quick rundown of the topics I'm going to cover here. I'm going to start with a walkthrough of some of the solutions and systems we developed for large-scale destruction in a multiplayer environment in LEGO Fortnite, building high-fidelity cloth using our new clothing tools and pipelines. I'll look at CVD, the chaos visual debugger, and finally some other general memory and performance improvements we've made in support of all of these efforts. First up is using chaos to simulate large-scale destruction. It's a problem space we had to approach recently for Fortnite, where we have a large open world networked to multiple clients with large amounts of destruction from tiny objects up to full dynamic buildings. Each player also needs to be able to modify and interact with any simulated object within the world. There were a lot of challenges in realizing this physically active world, and these are a few that we'll go through today. First, we needed to have a robust asset workflow that would let us build a huge range of destructible assets in a repeatable and non-destructive manner, pun definitely intended. Once we had the assets, we needed to build a way for them to be connected to each other into larger structures and to further connect to the world. When the structures got really big, we had to worry a lot more about scalability. We had a lot of particles and shapes moving around. We needed to bring down our runtime and memory costs. And finally, we had to consider how it was all networked and how gameplay-affecting actions are represented to multiple players while they could potentially all be interacting with the simulation simultaneously. So we needed an asset to hold the object data. Geometry collections should be familiar to anyone using destruction with chaos physics currently. They are a collection of physics bodies that all update and render together in a lightweight fashion. They render each piece rigidly skinned, and we can use clustering levels to group them together into larger masses for simulation. Next, we needed a way to ingest a lot of these assets and fracture them in a controllable and non-destructive way. We built a pipeline on top of data flow, which is a node-based data transformer that allows us to modularize the fracture tools and apply them in a repeatable manner over many assets. We can add logic, for example, clustering elements based on their level, their count, or density. We can configure and generate convex hulls. We can add overrides for special cases. One that we had in particular was doors, where you want to preserve the shape of the door more accurately for players that want to walk through them. A utility blueprint then executes the data flow on a collection of assets, and it outputs at the end the final geometry collection and a blueprint actor ready for use to just be dragged and dropped into the game. Data flow for geometry collections and destruction is experimental for 5.4, with many future improvements planned. Once we have all of the assets, we've ingested them all, we've got all our blueprints, we need to place them in the world and then have them connect to each other and to the world itself. For this, we built a connectivity graph component and system for managing these connections. A decision we made for a more consistent world was to limit the destruction to be server authoritative, which means that only the server needs to keep track of the object connectivity. It isn't represented on the client at all. You can see some examples here of connected actors. It's an undirected graph that makes it easy and quick to look up connected objects and their islands and their world support. So we know very quickly whether an object is rooted to the ground or it needs to simulate dynamically. Building the graph tells us which objects need to be connected, but this is a gameplay system, so it doesn't actually do the connection. So next, we need to actually build that inside the physics scene. So to do this, we created a component called the cluster union. It's an object that can connect multiple geometry collections together as one physical body inside the physics scene. It's responsible for deciding which internal particles belong to which union, and it supports partial destruction. So in a destruction event, we don't have to release an entire geometry collection from the union when damage is applied to it. It can break in one area, and the rest of the component can remain attached to the cluster union. The system is a more feature-rich replacement for the cluster group feature you may have seen in previous engine versions, which allowed for edit time groups to really easily be set up, but didn't have a simple or quick mechanism for grouping things dynamically at runtime. Now that we have the geometry collections and they're able to connect to each other dynamically, simulating them becomes difficult. We have many particles and shapes moving around, especially for large dynamic buildings. If they're coming over and sort of resting on a height field, you have a lot of contacts. Collision detection just gets more expensive because of all those particles. We have many particles and shape pairs that are output from the broad and mid phases for collision detection. So to solve this, we incrementally simplify cluster unions. We wrap the collection in a convex hull over time. The shape is only used for simulation, so if you have a character running through the world, they're still querying against the actual geometry, which is still there, just disabled for simulation. You can see a few stages of the algorithm that we use here. So at the beginning, there are 14 boxes up here. That gets simplified down to 7, down to 4. And if you have it configured to go even further, you can go down to like 1 convex that wraps the whole thing, which is, that's a lot faster to simulate 1 convex hull versus the entire building. As we're building the convex hull, we use a volume heuristic just to decide whether we've deviated too far from how the geometry should look, and should we stop simplifying. So I think with the default setup, we'd probably end at stage 3 here. But to illustrate it, I've configured it to allow for infinite simplification, so you get the whole building. If you had a shape that was more complete rather than just a corner, and it still satisfied the volume heuristic, you would still get that whole single convex where it's appropriate to wrap it like that. So that's a lot of things that help the simulation run faster, but now we have a problem on the rendering side. Many geometry collections in the scene, they'll all be responsible for their own rendering. They'll have their own scene proxies. And that's generally because in a random fracture, if you've uniquely fractured a whole world, every piece will be unique. So we need unique vertex data and unique scene proxies to render them all. Not all geometry collections will have unique pieces, however. This is something we hit a lot because we had a lot of small repetitive pieces. But even in other contexts, if you imagine a barrel that you have, you've got a top and a bottom that are probably the same. All of the staves that make up the wall of the barrel, they're all probably the same, and there's probably between 20 and 30 of those. So in cases where we have a lot of shared geometry, we can do better. So we added ISM pooling to geometry collections, where multiple collections can share a pooled array of individual pieces, and then they get rendered as instances. It's a lot faster to render for large scenes, and what we can also do, if you have a scene that has an asset repeated many times, which is another situation we found ourselves in, we can take the root unbroken mesh, collapse that down to a single instance, and then render all of the instances in the world in one fell swoop. So here we've illustrated this here. We have 2 geometry collections. They each create an ISM renderer. Those renderers reference the shared pool. And here we have a sphere and a cube in both of those, so they're both bound to that instance. And we have the 2 unique instances there that just have 1. But as you add more to the scene, these pools fill up, and the rendering is a lot faster. During large destruction events, we often ended up with many smaller pieces breaking off from the cluster unions, and processing those for collisions against the world was quite a significant cost as well. So to mitigate this, we developed the idea of debris particles. These are non-root pieces of geometry collections that aren't connected to any other geometry. They're sort of the leaf nodes of the graph that makes up the building. In this illustration, each of these primitive shapes would be debris once they broke off. They no longer affect any gameplay systems, and they can't apply forces to other dynamic particles in the scene. We remove them from the external acceleration structure, so no scene queries will detect them outside of the physics thread. This saves on query and spatial acceleration update costs when you have lots of things moving around. The collision response for debris particles is modified such that if we hit something that isn't debris, we get that situation where no force is applied. The other object is seen as kinematic or infinitely massive in the collision, and we immediately go to just applying the force to the debris. If two debris particles hit each other, however, we use a normal response. So if you have two small particles that hit each other, they will appear to bounce off. But in this case, we had it set up so that this was client only. Everything that moved through the world was kinematic to the debris, and it saves a lot on the update costs when you've got lots of small pieces flying around. We also needed a buoyancy system that was adaptable to a wide variety of creations that the players could build. The gameplay takes place on an island with rivers, lakes, and oceans, so realistic water interactions were a must. The system had to be performant, and because it is physically based and it's in a project where we are using asynchronous physics, it had to run inside the physics thread. So the system collects the bounds of the objects that are intersecting the water plane, and we use a mid-phase collision modifier for that, so we get a callback from the physics simulation telling us about all the potential collisions with a water volume. We subdivide those bounds iteratively into a hierarchy, and we slowly refine an approximation of the submerged volume of the object, where its center of mass lies, and an approximation of the surface area of the object underneath the water. We use the volume and center of mass to create the buoyancy force on the object, and the surface area helps us work out drag and current forces when the object is in the water. If you build a boat and float it on a river, it should flow down the river towards a lake or an ocean. The system is available as a plugin named Buoyancy in 5.4, and it works with any rigid particle in the physics scene. And these two examples in the top, we have geometry collection and cluster unions. In the bottom, it's just static meshes. It's all based on you set up a system that knows this is a water volume, and it interacts with things that obey this filter, and we can apply buoyancy generically across all particles. Next, networking. I mentioned earlier that the destruction was server authoritative. Although the server is responsible for breaking events, the client still has simulation for objects, but doesn't do any breaking without the server telling it to. It means we might see a situation where an object bounces off a destructible, then a little while later, depending on what the round trip time is, the client might pick up the break, sort of like this, which isn't great because the client missed the event. We would have to try and correct this. Rebuilding the destructible object after the fact like this would have been very difficult. And the debris isn't there on the server, so we don't have a target state to correct to. So there's no real option. We have to roll it back and resimulate the event if we want the correct result. Prediction of the events would also have been problematic because with prediction, you might also be wrong, and in which case you still need to roll back the event. Instead, we use new predictive interpolation mode for our replication. We target a state that's slightly behind the server, roughly half of the round trip time, which means that the client receives the destruction events sort of just in time, or at least very close to the time when they would have been correct. So here's an example of how the scheme works for position and velocity. So in step one here, we take the two states. The current state here is ahead of the target state that we've been told the server is at. So first we calculate the difference here. That's the pos diff in white here. So we need to slow down the current state, and we need to make it turn slowly towards the target state. In step two, we divide that by the round trip time. So that is now a velocity that would take, in the time of the round trip, what we need to apply to make sure that we match the position of the target state if the server and the client were both at rest. Next, in step three, we calculate the difference between the current and target velocities. So this is the velocity contribution to the movement. Then down here in 4, we add it all together. So we add the position correction velocity from step 2, and we get this target velocity here in yellow, which would fully correct, very harshly fully correct the client. In step 5, we scale this down to a value that is sort of approaching the correct value, which helps us smoothly interpolate towards the target without overshooting. Finally, in step 6, we add in the scale velocity to the current velocity. That gives you here the final velocity for this one update here in white on the top left of that triangle. In between receiving new targets from the server, we extrapolated along the velocity by the delta time on the physics thread, and then we replace it when we get the new updates from the server. This is key to making the correction toward the target smooth, because we're approaching an extrapolated target that's slightly behind where the server should be. And as we're working in velocities here, we don't directly set the positions. We can avoid doing as many sort of large hard snaps unless the desync is very severe. This example here is for position and velocity, but we do similar logic for rotation and angular velocity. And you can choose this just in an actor. You've got the physics replication setting. You can now just switch it to predictive interpolation to see if this helps any situations that you're running into with physics networking. So I want to change up a little bit here and talk about some improvements to our clothing pipelines. You can still see here, this is a still from the Talisman demo we presented at GDC this year. One of the goals was to get very high quality garments simulating on a MetaHuman character all inside UEFN. The simulation team worked closely with the MetaHuman team to build and deploy a new pipeline that has greater user control and very high quality results. So some of the goals for the pipeline that we wanted to build: first of all, we wanted to break the dependency on skeletal meshes as the owner of the clothing data. Up until now, it's had to reside inside a skeletal mesh using the skeletal mesh tool editor and the clothing panel to create the data, and it was rendered through the skeletal mesh component scene proxy. Splitting it up allows us to control the asset independently while still sharing some of the functionality. We still have the skinned mesh component now as the shared base class between skeletal meshes and the clothing component, so we can share where it makes sense. It simplifies additions to the pipeline, separating the concerns between skeletal mesh and clothing, so we can build new functionality that's specific to clothing without affecting or impacting any skeletal mesh functionality. We also wanted to use Dataflow, the node-based transformation tool, to define non-destructive ingestion pipelines for clothing as well as destruction as it comes into Unreal. It enables us to still have custom setups, but we also have facilities for automatic LOD and automatic skinning, so we can automate more of the clothing setup. We also wanted to support the pipeline with a robust set of tools for managing panel-based cloth workflows, creating and painting attribute masks, and previewing everything all together. So here's an example use case in the new clothing tool. There are 4 main sections to the tool. First, at the bottom here, we have the data flow graph. And we've currently got selected an add weight map node. When you select that node, it activates this tool in the upper left here, which is the panel viewer, where you can see 2D panels and paint on 3D meshes. Here it's painting a map that will be used to drive the max distance attribute on the clothing asset, which controls which simulation verts are actively simulating and how far they can deviate from the skinned position of the cloth. On the right-hand side, we have detailed simulation and preview panels. The preview panel allows you to set animations and skeletal meshes and some more options to see in the preview viewport in the middle of the tool. Here, we're just going to select a walking animation. And we can preview the simulation on the character mesh. So you can see here, the simulation is running, and it's interacting with the character as it animates. So next, we'll turn on some of the visualizations. We'll have a look at the sim mesh rather than the render mesh. Turn on statistics, so we get some statistics that appear in the top left. And we'll turn on the collision layers, so we can see the collision generated by the character underneath. There's a lot of other options in there to visualize pretty much all of the parameters you could possibly want. And it'll all appear there in that preview viewport. So next we can take a look at a data flow for cloth. Not the same graph, slightly different graph, a bit simpler. So this is what a data flow looks like. It's a node-based asset. I think I've said a few times now that it's a data transformer. It describes transformations to an underlying data collection. So this is a relatively small simulation setup for clothing. It starts here at the top left. It pulls in 2 static meshes. We're only making 1 LOD here. We could import more, or we could generate simplified meshes from these base meshes. There are also static meshes. We don't need to have skinned meshes, skeletal meshes imported to do clothing anymore. It is still an option to do that, but here we've gone with static meshes. Because it's a static mesh import, we don't have any skin weights. So we have a transfer skin weights node now, which you can pipe in your character and the static meshes, and we can generate the skinning data either by closest point or in-painting methods. So we've got multiple different ways of binding those meshes together. Using this method, you could take one base static mesh and a bunch of characters and use a data flow to generate skinning data and clothing data for all of those characters. After that, we've got our weight maps. We add 3 weight maps here. They all then get put into the max distance and the backstop config nodes. Max distance was what we painted in the other example. Backstops are a way to have a cheap sort of sphere collision check per particle to make sure it's not crossing back through its skinned position and potentially penetrating the mesh underneath. After that, these are all different configuration options. Pretty much anything that the solver can have configured is exposed as a node inside Dataflow. Finally, we set up a physics asset to collect collision information over here and run it into a terminal node. The terminal node, when it is executed, will take all of this information, import all of the data, commit it to the clothing asset, and then that will be ready for use in Unreal. There's a much more in-depth walkthrough of this, setting up clothing and some example assets to experiment with over on the Epic developer community if you're interested in seeing more and learning how powerful Dataflow can be. Next, I'll run through a little bit more about how we made the captain asset that we've shown in that video before and the still at the beginning of this section. I mentioned earlier that we had a skeletal mesh import node alongside the static mesh import node. We also have a USD import node. And as we announced during the GDC show this year, we support an import pipeline now from Marvelous Designer. This is a quick look at the source asset here for the outfit that we used on this character. We used one of the stock MetaHuman bodies to build the garments around. When working in Marvelous, you can build your garments, of course, and you can also configure the simulation. When we export to USD, those simulation parameters are saved as a collection alongside the mesh data. And we use this as a basis for the solver configuration in Unreal once the import is complete. The import pipeline from Marvelous Designer is available in Unreal 5.4 in beta. So if you're looking to create some high-fidelity realistic garments for an Unreal project, you can use Marvelous Designer to help you do that and import it to Unreal and process it further after import with Dataflow. Once you have the asset in Unreal, you can configure it and it's ready to use. You can also take the asset and further migrate it over to UEFN, similar to the process we used to build the Talisman demo if your project is also UEFN-based. The end-to-end process is to create your initial clothing in your DCC tool of choice, create a data flow to import it into Unreal, and then build your final clothing asset. You can then use the migration action in the content browser of Unreal to send your clothing assets over to the content folder of a UEFN project. For both Unreal Engine and UEFN, once you have the clothing asset, you'll need to add a chaos cloth component to your actor. Point that at the clothing asset, and then everything should work fine in-game. If your cloth component's parent is a skeletal mesh component, then the skinned portion of the clothing simulation will automatically follow the animation of the skeletal mesh component. If it was brought in from a static mesh, that'll be via the transfer skin weights. If it came in from a skeletal mesh, the skin weights will already be there. So putting it all together, we have a final clothing setup for the Talisman character. The jacket is 100% simulated, and there is a kinematic collider that represents the body underneath the mesh. We had a custom-tuned mesh and simulation for LOD0, and we relied on the automation nodes to handle the simulation meshes for the lower LODs. The LOD0 simulation is targeting roughly a 30 frames per second update rate, and the lower LODs range from 40 to 60. The tools here really let you use whatever budget you have for clothing in the best way possible and simplifies the setup of clothing overall. Different configurations can be built for different situations with the ability to override behaviors and complexity for cutscenes, for in-game action sequences, separate them per platform. So the setups can be tweaked and developed, and because it's a non-destructive pipeline, you can really dial in a solution that fits your needs without committing to having to re-import everything and start again. The video here shows the LOD0 simulation and render meshes for the captain. But we'll have a quick look at the remeshing just to show you how that works as well. Dataflow has a remesh node, which allows for automatic generation of lower detail meshes. So you input a target percentage and some other parameters of the vertex count for the input mesh, and we generate an output mesh. It can be applied to the render mesh and the sim mesh, or just one or the other. So you can keep the same render mesh, but lower the simulation LODs over the LODs of the character. For the creation of the LODs for the captain in the Talisman demo, we handcrafted the render meshes for all of the LODs, but we used this automation for all of the simulation meshes. These here are the LOD 0, 1, and 2 simulation meshes that we used on that character. So that's a brief rundown of the new clothing pipeline and how we put together that character for the demo. Hopefully it gives you a bit of an insight into the power of data flow. It can be used in many different situations, from destruction to cloth, and we hope more in the future. And now that we have these new ways to import, generate, and configure clothing, we hope it's easier than ever to create fantastic clothing simulations that are hyper-realistic for your characters. As I mentioned before, there is some more in-depth information, some tutorials, some walkthroughs, some example assets, all on the developer community if it's something you want to look into for your projects. Next, we'll take a look at the new visual debugger, Chaos Visual Debugger, or CVD. This is a new tool that we released in beta with 5.4 that allows a very deep level of inspection of the behavior of any chaos scene. It's accessible in any editor build just by looking under Tools, then Debug, then Chaos Visual Debugger. And it allows for capture and playback of any physics scene in an Unreal game in a non-shipping configuration. So we serialize the state of the physics scene directly from Chaos, straight from the physics engine, making sure to capture the exact data as the physics system sees it from any running Unreal instance. There's a small amount of overhead in having it compiled in because we are injecting some extra code here, which is why we compile it all out in the shipping configuration. The data transport system for the CVD tool is built on top of Trace, which is what Unreal Insight and other debuggers use inside Unreal. It gives us the benefit of a robust and hyper-performant transport layer that's already been tried and tested. We can record and view a session live from a build, or record it directly to a file without running the debugger directly, so it can be viewed or shared later. Connections can be easily made over the network to any game instance that's capable of using Trace with a simple console command, shown up here. Running that will identify the client to a running instance of CVD, and when you click Connect to Session, you should see it as a live session in that window. It's cross-platform, works everywhere that Trace works, so you should be able to record and debug sessions live from a running console build, for example, and inspect it on your editor. In addition to recording the state the physics system sees, the state can be captured at various stages throughout the update. It's not just before and after physics. The begin phase of the physics update, this is actually just a quick overview of how Chaos updates. The begin phase will be before we've applied anything at all. This is how we start the physics update. Then we go into the integrate phase. This will move the particles, the shapes forward in time. This might put them into intersection at this point. We'll later detect those intersections and solve them. Next up, we run the collision detection pipeline. So during the broad phase, we work out which particles may have overlaps, very coarsely using bounding boxes. In the narrow phase, we'll get exactly which particles collide and how they collide, and build a contact manifold to describe the collision. At pre-solve, we should have all of the constraints, but what we don't have is any adjustments to the particles yet. So the constraints are fully formed but not applied. And then at post-solve, we apply all of the updates, and that's sort of the final result for that update frame. The end stage has a few extra things. If you're using resimulation or we have late probe collisions, they're also processed right at the end. So we can have all of these stages individually represented if you enable their data channels inside CVD. Once the data is recorded, there are many settings for visualization, so you can try and get more information out of the scene once it's been loaded in. We have contacts, scene queries, geometry, and joints currently. We expect that more systems that are inside Chaos will be using this in the future, and this will expand over time. So to illustrate how the tool looks and works, I'll run through a quick example using Lyra. So this is the Lyra sample game, and I'll just use it as an example here. For anyone unfamiliar with Lyra, it's a sample we publish of a feature-rich multiplayer shooter as an example of how to get started with Unreal Engine. So we're going to run around a little bit. This is actually the pre-game, so there's no damage being dealt at the moment. So right now we've got a lot of kinematic objects running around, a lot of static geometry, simple geometry, complex geometry. When the round actually starts properly and the characters can damage each other, they will actually go into a dynamic ragdoll state in support of the fizzling out elimination effect that we have. So this is the round proper now, and you can see I'm taking some damage here. And we'll see some, we can't quite see the ragdolls happening, but some characters are being eliminated over here. So we've had at least one elimination now. So I'll switch over to what this scene looks like in the debugger. So this is what we see when we start it up. It should be a general layout that people are familiar with. We have a details panel over on the right here that sort of will represent all of the physics data. At the bottom, we have a new bit of UI here. This is the solver timeline. We have an overall timeline for all loaded captures, so you can sort of scrub through and see what's going on. And then we have individual tracks for each solver. This is quite useful if, for example, you are loading the client and server solvers side by side, so you can see what's happening on the client and what's happening on the server and where they may desync or disagree. And towards the right, just on this little part of the UI here, this is where you would step through those different stages in the physics update. If you're, for example, suspecting there's a problem after integration, but before we've applied the results, you would enable the data channel and select over here to see the results of that. So here we can just see a flat plane. This is the main menu because I started the capture immediately when the game launched. A little bit later, we get some geometry popping in the back. That's the environment that sits behind the menu. And then a little bit later, we load into that level there, which is the expanse map. So the camera's in the same position. It's just that everything's now loaded in. But it's looking a little bit gray, so we'll turn on some of the visualizations. This view here has static objects in green, kinematics are blue, and if there were any in this view, the dynamics would be yellow or red if they were sleeping. We have other different other colorization modes for different parameters, so you could see like shape types if you want to see like all of the spheres and boxes and convexes all separated by color. We could also separate it by server and client, so you could sort of really see that difference if you've loaded both of them into the tool. This is a section of the start of the round playing in CVD. We've got the red team who's coming out here with the spawn point, and that's my player character running over that sky bridge over there. This is the blue team coming out, and if you watch the character in the middle there, it's just been eliminated and fallen behind that pillar. So we can take a look at that character. It's currently bright yellow because it's still simulating. It's caught it when it's still simulating and then turned on the contact mode so we can see all of the contacts that are generated for each of the bodies inside the ragdoll there. So if you select one of those contacts, we get the contact view, data view over on the right-hand side here. So I've got a slightly zoomed in version of that, but there's still a lot of data. This is pretty much all of the internal properties that Chaos requires to solve a collision, and you can see them all in CVD. So we can see how much push out and impulse data we've had here to apply to the collision to solve that particular contact. We have all of the CCD data, all of the shapes and materials. You can also fully inspect the manifold that was generated, so you can see all of the manifold points, all of the normals at all those points. If you suspect that our narrow phase has misidentified something, you can go and have a look inside the manifold and see. Hopefully this kind of deep inspection will give you a good head start on diagnosing any issues you've encountered with collisions on simulation geometry. We actually also have, there are two buttons up here on collisions, so you can easily jump to each shape that's in the, each particle that's part of that collision, so you can see it in the viewport. We also have similar data for scene queries, so we'll take a quick look at scene queries. This is one of the characters running across the main hallway of the map. I've selected the collision capsule, so that's what's represented in the data panel at the moment. As it moves around, we'll do a fair number of queries. The character mover will first do an overlap in place, and then it will do a sweep forward to see if it's a good place to go where it wants to go. Its desired location has to be free of collision for it to move forward. It will also sweep down through the ground just to try and identify the ground and make sure it doesn't need to transfer into a falling state. Beyond the movement of the capsule, the animation system is going to be querying the floor for foot planting and alignment information, and there's probably some other gameplay systems that are doing queries in and around characters. So when you turn on the scene query mode, it does get a bit busy if there's a lot of scene queries going on, but you can pretty much see all of the situations I call out there. You have this pale yellow overlap, which is the overlap in place. There is a blue sweep just ahead of that. That's the character trying to move by its velocity times delta time forward. And the one inside the ground is trying to look for the floor. And then we have a few raycasts around the characters for foot placement and for some other gameplay uses. So if we select one of the foot placement queries, we can inspect that as well. Has even more data than the collisions, because there's quite a lot of data in a query. So we have all the inputs that were provided to the query, and then we have the hit buffer that we returned back to the caller. We also show all of the visit data sort of down here for each of the particles that we visited inside the scene query itself. We use a visitor pattern to record the interactions and traverse the scene query structure. And in here you can look at everything that we touched through that query. All of the shapes that we had to have a look at, you can find out which one was the blocking hit, why it was the blocking hit, and which other shapes were considered. So if you're in your project, if you're getting a query result and you're hitting a sphere that you either didn't place there or you don't think should be there, you can take a look at this and try and work out, why was this picked as the blocking hit for this trace. So that's a very brief introduction to CVD. We hope it'll help you better understand what's going on under the hood inside Chaos and inside the physics engine. If you'd like some more detailed information and documentation, my colleague Sergio has written an in-depth user guide available on the Epic developer community titled Chaos Visual Debugger User Guide. It's pretty comprehensive and it covers pretty much all of the features that Chaos Visual Debugger has and how to use them. Next, I'd like to discuss some other general optimizations that we've made in support of all of these projects that we've been doing, and they should have a positive effect on memory and runtime for a lot of your simulations. The particles inside the physics scene are stored in an SOA, or structure of arrays format, which is a data-oriented container that attempts to keep data contiguous, but rather than by object, which would be an array of structs, it's by access pattern. This can give some CPU cache benefits to algorithms like particle integration, which is going to iterate through all of the particles, all of the positions, all of the velocities at the same time, but it's not going to care about geometry or friction. So if they were interleaved, you would fit less information on a single cache line. It's better if we can fit more of any given property within a cache line, as that will improve the throughput of algorithms that can take advantage of such a data layout. We notice when working on scenes with lots of geometry collections, which create a lot of particles and a lot of shapes, that a number of the properties were being stored at a higher precision than we probably needed for them. So they're all listed here on the right-hand side of this slide, and they're colored by type there. So the two rotations are quaternions, then we've got a bunch of vectors and some simple floats at the end there. Overall, it saves about 144 bytes per particle for every particle in every physics scene. Which, when you've got thousands and thousands of shapes, is quite a decent saving. In 5.4, we'll convert all of these types in place because they may have been saved inside some physics structures. Once they're saved again, everything will be in the narrower format going forward. Geometry collections are based on a type we call a managed array, which it allows for arbitrary storage of any attribute you want. You can attach and detach attributes over time. They can all be serialized into an asset. It can potentially sometimes obfuscate exactly what data is stored inside the geometry collection, inside the managed array. We have two collections that are available when you're running at runtime. We have the rest collection. This is what we save into the asset. It is an immutable initial state for the asset. And then we create a dynamic collection, and we create that from the rest collection. The dynamic collection is mutated by the simulation as it runs, as it updates, and as results are produced by the physics simulation. Some of the data that was stored in there was either unnecessary, as it could have been immutable, or we ended up storing it in multiple places. So we have a few examples here. After we've initialized the geometry collection, we don't need to keep the implicit geometry inside that collection anymore because we've essentially moved it into the particles, and it's now resident inside the physics scene. And if we were to recreate the components, if we were to re-register it, we would recreate the dynamic collection from the rest collection and have that data back and available. We're also tracking particles in multiple places. The collection had some way of tracking particles, and so did the scene proxy, the physics scene proxy in this case. So we could remove one set of particle tracking because we already had it available to us. Initial levels are indices, the same as the children and parent indices that were stored inside the collection. These were all immutable, and we could move them and keep them on the rest collection, so we're not duplicating data between the two. So we removed a bunch of unnecessary attributes for the geometry collection, and again, the immutable data was removed from the dynamic collection because we could just go to the rest collection. We could also narrow some types. We tightened the underlying storage on a bunch of sort of enum and bit field flagged data fields, and reduced precision where possible on other values, such as relative transforms inside a geometry collection when it's at rest. Didn't need to cover the whole double precision space, so we could narrow those down. Some of the data arrays for the runtime simulation were also getting much larger than we required. We ran into a situation where we had a geometry collection that had maybe 1,000 particles in the actual authored asset, but we only simulated 100 of them because we brought in lots of small pieces, clustered them together, and only simulated the clusters. When we do that, we ended up with a sparse array with a lot of dead space inside it that we no longer required. So now we track the indices for the shapes. We've compressed that sparse array down at runtime to reduce the cost for the whole collection. So yes, if you have a situation where you have higher detail in your offline asset that you have in your runtime asset, this should reduce some of the runtime cost of spawning that geometry collection. And finally here, we don't need to have all the geometry up front. This is especially the case if you have a huge world made of many, many destructibles. At initialization time, what we were doing prior to this was creating all of the particles we'd need for runtime. We don't need to do that for most collections, most geometry collections, most destructibles until they break. We still can. It's now an option inside the component, but we can skip creating it until destruction happens, which reduces the overall memory load for complex scenes with many, many destructibles. There is a trade-off. You are now moving that initialization time cost to fracture time. When we're talking about fracture, breaking apart a geometry collection means that we need to dynamically recluster and activate new pieces. It'll usually involve at least one new particle being activated, and usually a lot more than that. Depending on how the asset is constructed, it might also allocate an internal cluster and activate the internal cluster instead. That's required when the break doesn't fully decompose a geometry collection along the cluster lines it already has inside the asset, so we need to create a new cluster to hold some of the pieces that break off. When a player is in control of game objects that cause destruction, like explosives, you could end up with a large number of breaks all happening at once. The explosion applies a strain to the particles within its radius, and then when the breaking model runs, it inspects the strain across the particles and activates anything that is above its strain limit. So we hit this with complex and large buildings made out of many, many parts. And the solution that we came up with here for very extreme scenes was to rate limit the breaking model. Rather than process every break that we can all at one point, we now limit the number of breaks we'll accept on any single frame or any single physics update. Anything beyond that limit is requeued pending a future frame. With this, we accept the maximum cost per frame for the breaking model, and we amortize the large cost of the break over time. The two variables, console variables listed up here at the top, are how we control these. The breaks allowed is the number of breaks that we'll attempt in any single frame. And the reschedule is how many we'll reschedule for future frames. Beyond that limit, we'll just not process those strained particles unless they get restrained again by the gameplay. So it's a bit more of an extreme effect in that we will stop doing breaking, but it can have a huge effect on these large scenes when we end up with an unreasonable amount of things to break all at once. So it does lead to a bit of a behavior change. Even when we're not hitting the reschedule limit, there is a bit of a behavior change. This here has no limits, so I strain every particle immediately in the simulation, and they all break apart pretty much immediately. Some of them look like they don't, but that's just because they're perfectly balanced. They did all break at the same time. When we put the limits on, you see now that a lot more of them make it down to the ground without breaking. Some break once they get there because they were rescheduled. So this simulation is running at about 60 frames a second, and I've got it set to 3 breaks. So we process 180 particles per second. And there's a clear difference in the behavior, but also a huge difference in the cost of the breaking model. And you amortize that cost over many, many frames. So it can be configured to look good for whatever you think is a reasonable amount of destruction for your project, and protect the physics thread, the physics update, from processing an unreasonable amount of breaks in a single frame. Also, up to 5.4, all of the geometries that we use for chaos particles were allocated as unique pointers, and the entire hierarchy was immutable once it was set on the particle. The particle took over ownership of the hierarchy. So if you wanted to replace one shape or modify one shape inside a particle, you would have to recreate that whole geometry, that whole hierarchy, with your change in place, and transfer the ownership to the particle. When we were experimenting with attaching and detaching, welding lots of shapes together, we realized that although the lifetime here is very clear, which is a good thing, it was too limiting in dynamic scenes due to the cost of recreating these hierarchies for modifications. Especially if you had a gameplay system that did multiple welds in a row, that would cause multiple recreations of the hierarchy within that particle. We've now moved to reference counting the geometries to make it much cheaper to move them, copy them, and modify them. So in-place modifications don't require that recreation anymore, and all of the geometry can be shallow copied where it's required, and the lifetime can be shared while that modification is going on. When we build connected objects that involve welding or clustering, it's so much faster, especially if you have large collections. A static mesh is only going to have usually 2 shapes. It's going to have its simple and its complex representation. But geometry collections and cluster unions can have hundreds to thousands of shapes inside the hierarchy. So that's where this kind of support becomes crucial. There's still some more areas that we'd like to address inside the geometry. For now, a lot of the geometries are single heap allocations rather than being pooled together, which isn't ideal when you come to then do collision detection and you have to iterate the shapes and there's a lot of indirection. So that's another thing that we plan to look into in the future. We're still focusing on geometry. Finally, we'll touch on a change that we made to the event processing for simulation events. Prior to 5.4, the only way you got events was a callback per event. For collision events, it's routed through the physics scene, and the physics scene will call the on-hit events on your actor if it was involved in a collision and you've registered for the events by checking simulation generates hit events on the actor. With large destruction scenes, it became very quickly apparent that the overhead for the per event system was quite large because we were jumping first through a virtual interface and then sometimes even further into blueprints for each event to aggregate them together to try and make decisions for audio. So for these use cases, we've added a new method that doesn't replace, but it sits alongside the per event model, which is the event relay. It's available from the physics scene, and it exposes delegates for each of the event types, and they're all dispatched to user code as a single buffer. So it can then be further filtered by user code, and we avoid doing those callbacks over and over for every element. We use this to centralize all of our collision and break events for audio processing. We filtered them, processed them in one place, and we gain a lot of time back doing this, rather than before we did need the whole collection, and we were slowly aggregating that per event until we knew that all the events had been consumed, and then processing them for audio. So it's not applicable to every use case. Sometimes you just need the actor that got hit to know that it got hit. But when you can make use of taking the whole collision buffer, it's much faster to use this method. And on the right here, this is just a small snippet about how you register to it. It's super simple. We just expose some multicast delegates off the event relay, and both systems are still available. So you can pick whichever method makes more sense for the use case you have. And that's everything from me. There's a lot more we couldn't really cover today or fit into this talk, but hopefully it gives you good insight into sort of the improvements that we've been making, and how that works for Unreal in general. We'll be continuing to push the boundaries on new physics features and better performance, so you expect to see more improvements in the future.